We've got our notebook ready, and the agenda is to analyze the drawback of the train test split procedure for model evaluation, and then move over to a mitigation of this drawback known as k-fold cross-validation. How cross-validation can be used for selecting tuning parameters, choosing between models, and selection of features is something that we'll check out next. And we'll also check out what are some possible improvements to this technique. Let's review some of the model evaluation procedures that we've already seen. Now, I know we haven't gone through a great depth of details on this, but I'm sure you're aware of these terms and I can use them to step on to cross-validation. So basically, the motivation here is that we need a way to choose between machine learning models. The goal is to estimate the likely performance of a model on out of sample data. The initial idea was to train and test on the same data, but maximizing training accuracy rewards overly complex models which overfit the training data. The alternative idea was to do train test split. So we split the dataset into two pieces so that the model can be trained and tested on different data. Testing accuracy is a better estimate than training accuracy because the test data is something that the model was not trained on, so the model did not see the data coming. It was unknown data from the eyes of the model. So we were in a position to evaluate on how a model performs if the data is not within the training set that it has already seen before. But it provides a high variance estimate since changing which observations happen to be in the testing set can significantly change testing accuracy. We start off with our coding exercise. We do the imports. In this case, we are going to use the iris dataset, which comes right out of the scikit-learn datasets. We are going to use the train test split function from cross-validation, the logistic regression model that we have already seen before, and the metrics from scikit-learn module to evaluate our model. Once the data is loaded, we split it into x and y. The train test split is a function which, when given the x and the y, automatically creates the partitions for us, and the randoms underscore state equals 4 means these splits will be reproducible if the random space or the random state is kept constant. Once the split is done, we fit the data on the training set and we predict the data on the test set, and we measure the accuracies, compare it with the test predictions with the true values of the test data. So this is giving us a 92% accuracy on data that it has not seen, right? So notice that it was trained on the training set and it predicted on the test set. So having a good accuracy on the test set gives us a fair amount of confidence on how our model will perform when it sees out of sample data.